Hello, my name is Matthias Rost, and I'm going to talk about doing neural networks. This is based on a seminar that I forgot to record. So here we go again. So I will be talking about neural networks. And when people typically present neural networks, they show pictures of nodes that are connected to each other in various ways. We can also talk about how a neural network is a mathematical abstraction of our brains and how our brains work. But those explanations kind of hide what they actually are and what they actually do. At the end of the day, a neural network is software running on your computer. But that software is doing something perhaps atypical to what software does. But in order to implement neural networks, it is just code that we are writing and that's running in our machines. So in this talk, I'm going to explain and show neural networks through code to show what they actually are and what's involved with doing neural networks. So I will follow this structure. I will start with some neural network basics. I will talk about inputs and outputs, weights and biases. I will explain backpropagation, and I will explain stochastic gradient descent. They are typically quite advanced topics and explained in complicated ways, but I hope I will show that they are actually very, very simple and basic in practice. I will then use this knowledge to do image classification. So we're going to build a neural network that's capable of the task of image classification. And then we're going to expand on that and do image generation using generative adversarial networks. Okay, so let's get started. Well, neural networks are basically, there are some inputs and there are some outputs. Okay, and all these inputs and outputs are all numbers. Everything in neural networks is numbers. So let's start by defining some inputs. So we're going to use the variable x1, and we're going to set it to a number. Let's put it to 3.0. Okay, and then we have another input, x2, and we set it to 4.0. Here it's worthwhile mentioning as well, we're writing Python code here. And I'm also going to be using something called Copilot. Now, Copilot is it's a tool that helps us write code. So it will give suggestions saying, I think you're trying to write this code. It's an AI that's using a language model for code. So I will be using that quite a lot, and I will explain when I do. We just saw it now, and it suggested 4.0, so we will use that. Okay, we can now define an output, say y, and Copilot is suggesting x1 plus x2. So let's go with that. So this is a very, very simple neural network. It's basically a neural network. And we can see what the value of y is. What is the output when the input is 3 and 4? Well, it's just 3 plus 4. It's 7, as we can see here. Okay. But this is not really a neural network that can learn anything. So let's add to it. So we'll also add some number here. We multiply x by w1, and we multiply x2 by w2. We also add a constant b. Okay, so b and w2 and w1 are all numbers. But what are those numbers? Well, we don't really know. Okay, we want to actually learn what those numbers are. Well, let's just pick some numbers. So we could pick some numbers, 0.5. We're picking these all randomly. We're letting Copilot suggest them. So what output do we get now? 2.5. But 2.5 really doesn't mean anything. We don't really have a meaning for our inputs either, but the output we definitely don't know because we just pick these arbitrarily. But since we're picking these arbitrarily, we will actually be picking them completely at random. So we will be using something called torch. So before we go any further, I will import torch. Let's do it here. And torch is just a framework for allowing us to do machine learning and neural networks and that sort of thing. And with torch, we get a way of getting a random number. So here we get one randomly number, and it's normally distributed. That's why there's an n here. So we get another one for our w2, and we get another one for our b's. So here we have 3 random numbers. So now if we execute this, we get 2.1488. If we run it again, we get a different number. And we can run it again and again and again. And obviously each time we get a new random number because our weights and biases, as they are called, are all random. Okay. Another thing worth mentioning here is that these numbers are not just numbers, they're tensors. If we actually print W1, we will see that W1 is a tensor. So we should really make these numbers. We can keep them as 3 and 4, but we make them into tensors because we're going to have to do that later on. So we'll do this. So you might wonder, what is a tensor? Well, basically a tensor, it can be a scalar, or it can be a list of numbers, what we typically call a vector. It can also be a list of numbers. It can also be a list of numbers, and so on and so forth. So it's a way of describing lists of numbers, and that Torch can handle in good ways. And it will also give us some nice functionalities when we use tensors. So that's how we do it. And when we have an expression with tensors, y is also going to be a tensor. That's what we see, that y is a tensor, right? And we can see the scalar tensor is actually just a list of one element in it. So that's what we get. If we don't want to see it as a tensor, we can say item. Okay. So enough of that. Okay, so what is it actually we are doing, and why do we pick these at random, and what does this actually mean? Well, we will get some meaning later on. We won't get any meaning just now. But what we can do now is to say that we want to actually accomplish something. Let's say we want y to be 0. Okay, so how can we get y to be 0? Well, since these are assigned randomly, we could just run this for a while until it gets close to 0. That was almost 0. You can run it again and again and again. This is a very tedious process. So this is fairly small. Is it almost 0? Maybe. But maybe we want to have a much more, a better way, a more systematic way of making it 0. And one way of doing that is to define another function which expresses when y is 0. Okay? And one way of doing this is not but doing what Copilot wants, but to say that y squared. Why is this a good expression? Well, because L is going to be the smallest when y is 0. Why is this? Well, we can try and plot a square function. So we can say plot a quadratic function. I'm doing this just because it's faster to do this using Copilot. There we go. So here we have a quadratic function. So on the y-axis is actually x squared, and on the x-axis is x. So we can see here that when x is 0, this function is the smallest. So that's basically what we're doing. Okay. So if we can find a way to minimize L, to get L to be as small as possible, and the smallest value possible for L is 0. But what that will mean for y is that y is going to be 0. But y is not restricted to being the minimal 0. It can go from -infinity to infinity, depending on what w's and b's are. So this is a way of saying, well, if we can minimize this function, then y will become close to 0. So the question then is, how can we minimize this function? Well, that's where gradient descent comes in. Okay, so what is gradient descent is? Well, gradient descent is a way of changing these w's and b's in such a way that L becomes smaller or bigger. Okay, and the way we want to change W1 and W2 is in the way so that L becomes smaller. So what we could do here is we could just change W1. Right, so let's just add some value, some small number. Have to be small, but let's do that, and we have to say data, because W1 is going to contain more than just the number, so we need to do this. So let's add some number to it. Sorry, first we also need to separate this little block here. Let's do that, and we initialize the weights, and now we can rerun this code without actually having to reinitialize our w's and b's, because we want to change them, and so we don't want them to reset itself all the time. So if we do this and run show L is 3.234, and we can run it again, and again it's going to be the same number because all the x's and y's and b's are the same. But let's now say that we increase W1. How does L change? Well, it become larger. So that's obviously not good. So we should make it smaller. Let's decrease it again, and we get back to the original value. But then we can decrease W1 again and see if do we now get it smaller. It did, right? So let's keep going. It's getting smaller. We can keep doing this. So the question is, how small should we make it? Maybe we should decrease it by 1, because it becomes even smaller then. Now it became bigger again. Okay. So as you can tell, it's probably not the best way of doing this. And also we're only changing W1 here and not W2. Again, surely there must be a more systematic way of doing this. But it has to do with we're figuring out how should we change W1, W2, and B. And that is where gradient descent comes in. So gradient descent basically says that, well, if we can figure out the gradients for W1 and W2 and B, the gradient is essentially to what degree a change in W's will affect L. So with that, we can update our weights. We can change W's based on their gradients, and that will affect L. So the question becomes, how do we calculate our gradients? Well, in Torch, that's very simple. That's what this expression does. So running backward will calculate the gradients for those values, for those tensors that we say that we want to have gradients for. So we need to add something here. We need to say require grad true. Same thing here, require grad true. What this will do is that for our W1, W2, and B, this expression backward will calculate the gradients for those values. And we're going to call these parameters. Okay. So if we run this now, oh, sorry, I need to initialize this and then we can run it. We can actually see that W has a value for its gradient. It's 18.4. We get the W2 and B also have gradients. And we can use these values for the gradients, which were calculated with this backward call, to update them. So the way we want to update them is that we want to say that W1 is going to be subtract a small number of the gradient. So the gradient multiplied by a small number, because we don't want to go all the way. We don't have to subtract 18.4, but in this case, it will be at least 0.1. Okay, that's what's basically gradient descent is. And then we want to do this for W2 and B. And this is an update, or this is actually gradient descent. Now, one thing we need to do as well is before we run backwards, the way backward is calculating these gradients is that it will increase the gradient by the new gradient. So we need to reset the gradients to be 0. And the way of doing that is by setting it to none. So we're resetting the gradients, and then we calculate the gradients, and then we use these gradients to do this. And this is actually what's called backpropagation. It's just a function call in Torch. And I'm not going to go through exactly what this does. We could do that in a separate video, perhaps. But now, if we run this, and we can actually output L, so we can see what L is. And we can remove this. So L is 9.4. If we run it again, it's going to be 2.1. We can run it again, 0.5. Run it again, and again, and again, and again, and again. And what we can see here is it's getting smaller and smaller and smaller and smaller, because that's what gradient descent does for us. So we're basically moving in the opposite direction of how the function L increases in the direction of the gradients. So that's what we do. So it's going to increase in this direction. So we want to go backwards. That's what we subtract. But this is it. So this is backpropagation, and this is gradient descent. We can make this a little bit more generic by saying that instead of just having W1, W2, and B, we can create a list of parameters into which we put these parameters, W1, W2, and B. The reason for that is because now we can, instead of writing this, what we have to kind of address every single parameters, we can go through for P in parameters and set their gradients to none. And for gradient descent, we can do the same thing for all the parameters in parameters. Please increase. We change the value in the direction of the gradient. So this will be the same thing. And now it's reset the weights. We're starting at a very large number for L, and it's going smaller and smaller and smaller and smaller. So basically what we're doing here, we're optimizing L for a particular input, which is 3 and 4. And by optimizing L, we're accomplishing something for Y. So if this is our neural network, what we're saying is that we are trying to train it to output 0 when the input is 3 and 4. But does that have any meaning? Not really. All we're doing is just showing how we can do that, how we can optimize L. Okay, so let's do something more, slightly more meaningful, using basically the same code, but something a little bit more interesting. So let's create a data set. Let's get a data set to be a number of x's and x1s and x2s. Actually, what we want to do first, we actually want to rewrite this a little bit again. I skipped ahead there. So, because typically in neural network, we don't just have 1 or 2 or 3 even inputs, but rather we have a lot of inputs. And we also have a lot of weights and biases. So instead of having to use these individually as x1, x2, x3, and so on, we instead put all of them into one tensor. That is a list of numbers. So into just one input x. Okay, so x is now a list of 3 and 4. And we can still get x1 by saying x0, x2 equals x1. Bear in mind that in Python we have 0 indexed in this 0 indexing. But it's the same thing. And for w's, we can do exactly the same thing. And here, instead of saying we want to have one random number, we of course take 2 random numbers. And our b is the same. And for our parameters, we no longer have w1 and 2, we just have a list of these numbers. But this will work just as fine. We also need to change our function here. It's our network, which is actually called our forward pass. This is how we move our data into our network to get an output. So now we no longer have x1 and w's, but instead we're going to write x at w. So this is what we refer to as a matrix multiplication. Now, neither of these are matrices yet, but they will be. So we write it in this way. And in this instance, it will be a dot product of x and w. This will be the same. So that's just a refactorization of basically the same thing. So we have the same functionality. So now what we're doing here was we're creating a data set, which is just a list of 100 numbers that have 2 numbers in them. So if we just get, let's show this, let's say we take 2 numbers and we print what it is. So it's just 10 pairs of numbers. So each of these pairs are going to be what we called before x1 and x2. Okay, but we have 10 of those just because we have 10 here. We can do 100 instead, which was going to be much more interesting. We could print those, but there's no need to do that. Okay, so that's our input data set. I also want to have something called labels of them. Okay, what do we want the network to say that this is? We want to classify them as something. We're gonna classify them as 0 or 1. And we'll use this expression from Copilot. What does it say? It says that the label will be 1 if x0 is greater than x1, and otherwise it will be 0. Okay. So then we can ask ourselves, what does that look like? Okay. Plot the data. So again, we'll let Copilot do that for us. It looks like this, and it's quite hard to see exactly, although you can hint it. But if we just add this to 1,000, it becomes a little bit more dense. So basically, there seems to be a line here separating 2 types of data. So data in this area is going to be purple, and data in this area is going to be yellow. Okay. So whenever x1 is greater than x2, it's going to be purple. Otherwise, it's going to be yellow. Okay, so that's our data set. And what we want to do now is we want to create a neural network that we can train such that if it's given a data point on this plane, it's going to be able to tell us whether it should be purple or yellow. So which a data point randomly selected, the network will be able to say if it is in this area or in this area. Okay, so we have data and labels. So what we can do then is that instead of our input x being 3 or 4, we can set it to be one of the data points. And we start with our just first data point, so data 0. Okay, so x is just one of these numbers, x1 and x2. And our corresponding label will be the label 0 that corresponds to our data point 0. Okay, so I have x and label. There are x and our label. So since x1 is not bigger than x2, it's 0. Okay. And what we want to do now is that we want to have our network, which is also going to be these new weights, right? So we need some sort of parameters for our network. So we're going to have weights. It's just going to be this, just as before. It's going to be the same. So we have our weight matrix and our B's, or our weights and our B's. Here we have declared our inputs, and then our output is going to be just as before. Okay. But then what we want to say, we don't want y to just be from -infinity to infinity. What we can do is actually we can put this through what's called an activation function that basically tries to get our y to be either 0 or 1. It kind of pushes it to 0 or 1. And we do that using a sigmoid function, forge.sigmoid. And it will basically, a very small y will be 0 and a very large y will be 1. That's what we'll do. Okay, so now we have our output from our network. And we can, of course, look at what the output is for this completely untrained network with random weights, 0.6897. And we can think about how do we want to interpret that, because we want the network to say whether it's in this data set or in this data set. Is it purple or is it yellow? So we can say here that, okay, if it's larger than 0.5, we can interpret that as being part of this data set. So basically, that should be interpreted as 1. And if it's smaller than 0.5, then we can interpret this as 0, meaning it's part of this data set. So that's just the way we can choose to interpret this. But hopefully we will get numbers that are closer to 1 and closer to 0. Okay. So then how do we train this? Well, we need to define this, what we can now call an objective function, L, and say that, well, what we did before was that we want so if the label was 0, we could just say that it should be y2, right? But since it now depends on the label, well, one simple way of doing that is just subtracted by label. Because what does this mean? Well, it means that if label is 1, the smallest value for this is when y is 1, because then this expression becomes 0. And when label is 0, well, all that's left is y. So this will say that we want to optimize y to become as close to label as possible, basically to become label, right? So for this data point, optimizing this would do the same thing as we did before, where x1 and x2 was 3 and 4. So if we just now run, well, first we need to reset these. So we want to go 4p in parameters that we of course have to define first. Parameters equals our w and p. Then we can do this, parameters, and reset the gradients. We can run backwards. We can then do our gradient descent by just changing the our weights or our parameters. So again, we have backpropagation. Again, we have gradient descent. This is exactly like before. The only things that have changed is our L, so our objective function, and also we added this activation function because I want our y's to be closer to 0 or 1. All right, so this code is nice. We can separate this block. So we have our initialization here, weights and biases and parameters. And here we have our network and our training of the network. And I mean, we could run this as it is. We can see what L is and see if it becomes smaller. I guess I didn't run this. So, okay, 0.05 and 0.05, it gets smaller, it gets smaller, it gets smaller. Now, for this one, I think our number here is possibly too small. And I should say, this number is typically referred to as our learning rate. We shorten that by LR. So we can set that to 0.1, which is slightly bigger. We can see what happens if we do it then. And L becomes smaller and smaller, but not that small, because it started out pretty big or pretty small already. So let's start, see if we can get it to bigger from the start. No, can't. Okay. It's already too small because our X is quite small. The X's are just between 0 and 1. But it is getting smaller by small steps. So that's promised. But this is completely pointless if we just do this for one data point. All this will do is train for whichever data point it is in this field to correctly classify that one. It won't do anything with all the other data points. It won't learn this relationship in the data. So how do we do that? Well, so instead of just doing it for the one of them, maybe we can go through all of them. That as well. Let's not do this. So instead of now taking the first one, we take the ith data point and the ith label, going through all the data in our data set. And instead of printing L, because that will just print us L numbers, we can record them and then we can plot them. So here we just put our L's in a list, and here we plot L's. Let's see what that is. It does this. So what we're seeing here is basically what is the L for each data point as we move across our data set. So we're showing it one number and we get a value here for L. If it's completely wrong, it should be 1. And if it's completely right, it should be 0. That's kind of the nature of it. And at the beginning, it kind of fluctuates quite a lot, right? It doesn't really know what it's doing. It hasn't learned anything yet. And as we move through our data set, you see that the span here is getting smaller and smaller and smaller. So something seems to be happening. You can also see here, once we get to a fairly high kind of thing, it's starting to perhaps decrease a little bit. So this is what we typically use. This is the plot of our L, of our objective function. Okay. So how can we make this look nicer? How can we make this behave nicer? And perhaps, what does this loss function mean? Well, we'll get to that. But there are better ways of doing this. Instead of just showing this one number at a time, we can show it more numbers at a time. If we were to be completely accurate, what gradient descent really is that what we should be doing if we're doing gradient descent is show the entire data set to this network, figure out what the gradients are for the entire data set, and then update the parameters according to the gradients when they're calculated for the whole data set. And we're just showing it one data point at a time. And we could do this because this is a very simple set, and we can do this for all the data points, but we're not going to do that. Instead, what we can do is we can say that, okay, so instead of just taking one number, what happens if we take more than one? Let's say 10. So what this is, So what this is saying is that it doesn't take just one number. It takes all the numbers from the index I to the index I colon 10. So if we take this and see what that looks like, we can set I to be 0. And then we can see what X and label is. So X is not just one pair of numbers. It's instead, again, 10 pairs of numbers. For our labels, we have a list of numbers, the list of labels that are corresponding to these data points. Okay, so we got that. That's good. But then the question is, what happens to our outputs? What happens to our actual network? If we're running these X's and labels, or X's right now, through our network, what happens to Y? Well, because of how these operators are defined, it's actually going to do this essentially per data point in X. So it's going to take each pair in X, run it through our we'll multiply it by our weights and increase the bias. And it's going to give us 10 y's. And the same thing for a sigmoid function, it will run sigmoid per element in the list now of numbers. So if we show y, this is going to give us 10 numbers. So this is going to be the output for each of the inputs. So that's a nice little feature. But lastly, what happens to our objective function, L? Because L here should tell us how well is this network working? Because it gives us a way of optimizing a network. So how well is the network working? And then we optimize the network to work better, right? We improve it using backpropagation and gradient descent. So what is L now? Oh yeah, sorry about that. So here's a saying that unsupported operands, tensor, and list. And it's because label here is not a tensor. We could put it into a tensor here, but what I'm going to do is I'm going to update our data to say that labels here should actually be a tensor. So I've done that mistake many times, and I never learn. Our data set looks the same, of course. We don't need to update our parameters. We just need to run this. So now labels is a tensor, y is a tensor, and this will be nice. So L is now a list of basically how well the network is working per data point. But we can't optimize that, or we don't want to optimize that. We could optimize it then per L, perhaps, but could we not combine this into an expression such that we optimize the whole network for all the data points? And really what we want to do is that we want all these L's to be as small as possible. So we can just sum these. Because if they're all small, well, the sum will be small. And if one of the L's is large, well, the sum will be large. So we can just take this sum. And now we get one number. And that we can optimize. Okay? So the only thing we need to change in our expression here, now that we take in more than one value, is this. You take it as a sum of all the L's, if you will. Okay? So let's see what happens then. Let's just initialize the network and run this, and we see a much more smooth out little curve that looks a little bit better. The span is a little bit smaller and things look nicer. Okay, and this starts looking a little bit more promising. So we're now seeing that we are actually achieving a much better network. L is the expression for how good our network is. And it starts at a high number and it goes to a smaller number. So obviously it's improving. But the question then is, what does that mean that it's improving? And what it actually means is that it's getting better at classifying these data points. So we're showing it a data point from the data set, and it's getting better at actually saying that it's part of this data set. A point here is part of this data set, or that a point here is part of this data set, or of this class, if you will. So this is data points that are part of two different classes, purple and yellow, ones and zeros. Okay, so another way of evaluating this network, I can remove this, is to actually calculate the accuracy, meaning we can calculate how many of these points are accurately classified and how many of these are accurately classified. So we can see train accuracy, and we're gonna do this by letting our little friend Copilot do it for us. So now what's doing is that it actually does the thing that I said before. We're running this network for all the data points. Okay, so this just gives us 1,000 numbers. So it takes all the data points, runs it for the network. Here it's actually doing a neat little trick where it's interpreting these numbers as either 1 or 0 using the same sort of interpretation as we talked about before. So if x is larger than 0.5, then it's a 1. And if it's smaller than 0.5, it's a 0. Okay. And then we're saying if y is label, so labels is all our correctly labeled data points. If they are the same, that will generate a 1. And then we sum those. So this will give us how many are correct. How many correctly classified numbers do we have, or data points do we have? And then we divide it by the total number of data points. We can use data here instead. And this will give us a percentage. or a fraction of how many are correct versus how many there are to classify. So if we run this, we get 95.5% accuracy, which is pretty good. Just not too shabby. If you want to know what it looks like if we just completely untrained network, it should give us 50% because it has no idea what we're trying to do. It knows nothing about the data. So if we run this, 53.1. That's much closer to half. It seems to be skewed in one direction or another. If we reinitialize it again, we get another number, 33.9. And these are all just by chance because of how we are initializing these values into something random. 53.10 again. But if we train it, training, and then run it, we get 95%. And if we're not satisfied with that, we might see that maybe this can be improved. All we have done here is that we've shown this data, each data point in the data set, only once. What if we show it again and keep training it? Well, let's do that. And that's typically what's called an epoch. So we're going to write for epoch in range, and let's run it 5 times. So now we are running it for our data set once, and then we're running it again, and we're doing this 5 times. So let's just do that. We want to reinitialize it and do this, and we're going to say our graph is going to be much longer, and we can see how it behaves. Now we get a higher number, 97.6. So that's not so bad. Now, can we do this better? Yes, we can. Because typically what you would do, now we're running through this network, the same every epoch. We take the first data point and the first and the second and the third and the fourth and so on, 10 of them each at a time, but in the same order. What if we instead took random numbers? And we can do that. So we can calculate indexes like this. What this is doing is it calculates 10 random numbers between 0 and the number of data points we have. And what we can do, we can use these numbers as indexes. What that will do is that if is equal to, say, 2, 3, and 5, it will give the x will become the data points for data indexed by 2, 3, and 5. So it will basically take the second, the third, and the fifth element from data. And it will, of course, do the same thing for labels. So this will give us a random number of indices, and that will give us those random indexed data points. Now, if we were to run this instead, let's see what happens. This becomes a little bit more, it's a nicer noise, nicer looking noise. It looks more random. And let's see what happened to our accuracy. And we got a much better accuracy here. So 99.5, what does that actually mean? It means we get 5 wrong. And the reason why we get any wrong at all for this very simple set is because, well, it's really hard to kind of separate them when they're really close on this line. It's possible if we run this again that we might get 100, but it's not necessary. Now we got even 1 less, but it's very close. And that's typically the nature of neural networks. We get a probability, we get a very high chance of getting it right, but it's not always correct. But that might be. Okay, so this is looking promising. What have we learned here? Well, basically what this is called, when we take a random set of numbers from our data set, in this case we take 10, that is typically what's called batch, and the number of elements in the batch is called batch size. So we can initialize that as, say, 32. Most often we take a number that is a power of 2. 32 is 2 power 2 to the raised to 5. So that is what's called a mini batch. And when we use mini batches in gradient descent, that's what's called stochastic gradient descent. So we don't take the whole data set, but we take a stochastic sample of our data and run gradient descent on that. And that's what's called stochastic gradient descent. So, and that's how we learn, that's how we train a network. And what we're going to see is that this and this is never going to change throughout this whole talk. So for image classification, it's going to look the same, but also for generative adversarial networks that we'll see. This will look the same as well. And much of this will look the same as well, but we'll get to that. But so we've learned backpropagation, we learned gradient descent, we learned stochastic gradient descent through mini batches. And yeah, so I feel like we are feel prepared now to do some real stuff, because classifying these is not that exciting. And it's not that hard. And we could do this in a much better way without neural networks. But let's get to something where neural networks are actually quite good. So what we're going to do now is that we're going to do an image classifier. We're going to classify handwritten digits. So we are going to first actually going to import torch vision. We could do it downstairs, but we'll do it here. So we're going to get something called torch vision, and torch vision will give us a data set that is quite nice to use. So we're going to load data from something called an MNIST data set. And we're going to add a transform. So what is this doing? Oops, sorry about that. So we're using torch vision, and in it there is a bunch of data sets that it's typically used when you're working with neural networks, and we're going to use the MNIST dataset. That is a standardized dataset for doing different tests to see how things are behaving. So we're getting the training dataset. We'll get to that. We will download the data if it doesn't exist, and it will transform all these to tensors. So we get all the data points as tensors. So what does this dataset look like? Well, we can try and see if we can get Copilot to show us some images. Plot data. I don't know if that's going to work. Okay, so this will show us one image. So this will show us the first data point in our data set, and that's handwritten number 5, perhaps. This is perhaps a 0. How do we know which number we are supposed to see? I mean, we can read these numbers, right? It's a 4. But we also get that from our data set. So this is the second data set, and the second element in this data set is actually the class that it's belonging to. And the class is essentially, so we saw that we had do we have a 0 in the first data set? Yes. So we get 10 classes of images, and the classes are 0s or 1s or 2s or 3s or 4s. Perhaps we can do plot a grid of images. With a little bit of luck, this will all work out nicely, and we get to see some more numbers, right? So this is the MNIST dataset. This is a sample from the MNIST dataset. And what we're going to do, we also have the labels for these. We know this is a 4, we know this is a 9, we know this is a 3, and so on and so forth. And what we're going to do is that we're going to create a neural network that can be shown these numbers, this image, and tell us whether it's a 4 or some other number. They can see this number and say this is an 8, or this number and say this is a 6. And this is not trivial to do, but we'll see that using neural networks, it's actually fairly trivial to do, and you already know how to do it if I just told you how to do it. So let's get to it, right? So how do we declare a neural network? Well, we define some weights and biases, but perhaps before we need to figure out what is going to be the input to this network. And the input is going to be the image, and the image is really just 0s and 1s. So we can see that 0, 0 is actually just like not 0s and 1s, but it's numbers, right? And for each row, it's look like this. It's a number of 28 numbers, and we have 28 rows in the image. So the image is 28 by 28. And you can see a white dot is going to be number closer to 1, and a black dot is going to be 0. Okay, so we have a lot of black dots and we have some 1s. So, but we're not gonna show it rows and columns, but we're just gonna take each row and put them next to each other to form just one long list of numbers. And we can do that by using this formula. What this will do is that we say we want to view this as just a list of 28 by 28 numbers. 28 by 28 is actually 784, because we will see that soon. But if we do that, we will just put this into one long list of numbers. Okay. So we're going to take this as our X, basically. That's going to be our input. So the input will be a list of numbers of 784 numbers. Okay. So we then need to have some corresponding W's. And we see here Copilot already knows what they are up to. So we'll give us this for us. So how are we going to, what kind of output do we want? So typically before we've had one number, 0 or 1, for whether it was belonging to class, basically whether it belonged to it should be a 1 or a 0, but we're doing a binary classification. In this case, we have 10 classes, 0, 1, 2, 3, and 4, and so on, up to 9. And what we want to then to do is actually get 10 outputs. And those outputs will signify what's the probability that this image belongs to class 0, how much is the probability that it belongs to class 1 and 2, and so on and so forth. So basically, some sort of probability distribution of how sure the network is that it's one of these numbers. And to do that, when we initialize our W's, we say that we have 10 numbers. And what essentially what this will be is that it will have 784 rows of 10 columns. So we'll have 10 numbers. And the way we can interpret it is instead, when we do X at, W plus B, we will not just get one number per input, but we will get 10 numbers per input. So that's how you can see this, right? Another word for these input values is features. So we have 784 input features, and we will get 10 output features from this network. Okay, so this will be our network. And then you can ask yourselves, do we want to do a sigmoid on this as well? Yeah, why not? Because we want this to be, the probability is either going to be 0 or some number between 0 and 1. So we can do a not softmax just yet, sigmoid for this. Okay, so this will be our forward pass of these numbers. Let's do this. Let's make sure we get our parameters, W's and B's. We do not know our X yet, but this is basically our network. It's basically the same as before. We have W's and we have B's. I mean, we have slightly more W's. We have 7,840, and we have 10 more B's, or 9 more B's, 10 times as many B's. But they are just our parameters, okay? And then we have our network. This is our forward pass. So that's this. And then we're going to need to have an objective function, right? So we need an L. And one way of doing this is, okay, we don't have a label yet, but we can have a, let's pretend we have a label. So if we had, let's put our X in here again. So this is this, and then we have a label to be the first data point. We're not going to use this later. Let's use it for now. So what do we do here? Well, so Y will give us 10 numbers between 0 and 1. And our label here will be just one number, 0, 1, 2, 3, or 5, 6. So this won't really work. Okay. So what is it actually we want to evaluate here? When is this network doing well? And when is it doing it poorly? Well, basically, our Y, we can look at our Y actually, I think. So we have 10 numbers, and we can interpret these numbers as the probability that they are belonging to a particular class. So in this case, we get some kind of silly numbers because we get this, it's 100% chance that this belongs to, this is a 0, 67% chance it's a 1, and 0.9% is a 2, and so on and so forth. So this doesn't really make sense. One way to turn this into a proper probability distribution is actually to run this through something called a softmax. You can just see what that looks like. Softmax Y. And what this will do is basically make this sum to 1. And if you have 10 numbers summing to 1, we can interpret them as a probability distribution that is one of the belonging to one of the classes. Okay, but again, it doesn't really know what number this is because it's a completely untrained network. So how can we be sure that it is belonging to that? Well, we have the label. Okay, so what number should this be? It should be a 5. Okay, so we should be able to look at the fifth number here. So 0, 1, 2, 3, 4, 5. We really want this number to be as close to 1 as possible. That's really our target. Because if this is 1, if we run this for a softmax and this becomes a 1, then these all other numbers become 0. Because if this adds to 1 and this is 1, well, all other numbers has to be 0. So if we were to use a softmax here, we're not going to do this, but let's do this for now. What we really just want to do is we want to say that the labels number in this list of outputs, we want that to be as close to 1 as possible. So we could think of saying that, well, let's just do this minus 1 because we want that to be 1, and then this is our objective function. And if we optimize L now, well, we want this to be 1. And that would do the trick. Unfortunately, if we do that, it's going to be not as nice to train as one might expect. It's not going to be as nice as it's been before. But this is really what we're saying here, that we're saying that we want to increase the probability that the probability of that the label is going to be as close to 1 as possible, is to say that we want to do something else. And this is basically called a binary cross entropy. So we want to calculate the binary cross entropy of Y with regards to our label. And we can do that. And let's see if it gives us the entropy. Sorry, not binary cross entropy. We want this to be cross entropy. So we have 10 classes. And we don't need to run softmax because cross entropy will do that for us. We also actually don't need to run sigmoid. It will do that for us as well. So now we're saying that our objective function is going to be the cross entropy. So we want to decrease or minimize the cross entropy. So what do we do then? Well, we do backpropagation. And Copilot already knows how to do that. And we want to do gradient descent. And Copilot knows how to do that. And that's it. Boom. We have a different objective function. And now when we use cross entropy, it's really just a measure of how much information we're losing. So this could be also called a loss. Well, let's not get ahead of ourselves. So this is just for the first data point, but we want to do this for all the data points in a data set. How can we do that? Well, so one way is to iterate over this data set. We could say that, just like before, for I in range and then length of our data, and we could try and generate a random batch of numbers and that sort of thing. But this is something we do quite often. So there is a way of doing this in Torch that is much simpler, and is using a data loader. So we're going to use a loader from Torch, where you specify what data will you want to pick these batches from. You want to say how big are the batches, and you can say that it's going to be a random permutation of numbers each time. So we'll basically create data coming from this loader will be in the batches of 32, and they will make sure that whenever you run through all the numbers in loader, it will be all the numbers in our data set in random order. Because now, instead of doing this manually, we can say that for our X and label in loader, that's it. But we see that we did something else here with our data. We didn't just take our data. So this is basically be what X is now. A label will be this. What we also did is reshape. Here it's called reshape, but we can also say that it's also X like this. And I've been indenting this wrong, so let's do this one. And reshape and view is essentially the same thing. We can use reshape. And we have a learning rate. Let's set that to 0.1 in this case, and let's change it here. Okay, and now we want to keep track of our else and see how actually this is behaving. We can add this here. Append item, and we can plot the else, and let's see what happens. So now what's happening, we're taking all the images from the data set, And just so you know, so the MNIST data set contains 60,000 of these images. It contains 6,000 zeros, 6,000 ones, 6,000 twos, 6,000 threes, 6,000 fours, etc. So 6,000 of each class. And we just now took all these numbers and showed it to our network. What does it mean to show it to the network? Well, we ran it through this function. And we tried to make sure it could classify these numbers. And our L here is going to show us how well it's behaving. And as you can see, at first it's really bad, and it quickly improves, and it improves, and it improves, and here it seems to be stabilizing itself. So once it's gone for one iteration, one epoch, it seems to be knowing a little bit better, more than it did beginning. But again, let's see if we can get the accuracy of this. So call it a train accuracy. So 0, start with 0. We get the X and label from the loader. We run this through the network. And then you can see here what's happening. It's using argmax here. Because what argmax will do is that which number is in the output will be the biggest. Because that's basically the highest probability. Which class is its most certain that this image belongs to? So which of the 10 hand-drawn digits does it think it is? And then again, we're doing the correct plus, and it's will, this will be a 1 if it's correct and 0 otherwise. The sum how many are correct, and then it will increase these correct numbers since we're doing this for mini batches. So correct will be how many of the 60,000 images will be correct divided by the 60,000 images. And let's see. 84% accuracy. Not too shabby. Let's see if we can improve it. Well, one way of doing it is just basically to run this again. If we don't reinitialize our weights and biases, we'll just run it again. So this will be our second epoch. Right, so 84% here. We're running it, training it, and then we check the accuracy. And let's see if it improves. So we had 84, now at 86. Do we dare to run it again and see what happens? So at 86, and now we get 87.9. It seems to be going strong. Let's try it again. I'm not going to run this many times more. It's just fun to see how high up we can get it using this extremely simple network. Okay, so 88. So it just keeps improving. And what we could do, of course, is to run this in a loop. So we say epoch in range, say 5. Let's reinitialize it and actually run it for 5. So now we're running it for 5 epochs. 1, 2, 3, 4, 5. And let's see if we can get this. But this is extremely simple. So all we're doing, we're taking all these pixels, stretching out a one long line in one row into one vector of numbers. We just multiply it by some numbers and taking and adding them, right? And we do that for each of the different classes. We get 10 different numbers. And we treat them as probabilities for how likely it is that a weighted sum of all the pixels says that it belongs to either of the classes. So now it's done. We see that it goes down to 0, perhaps. It didn't glow. Yes, with testing, evaluating the accuracy, 89%. So it's not too bad. I mean, it means that if we show it 100 numbers, then 90 of the numbers or 89 of the numbers will be correctly classified. And of course, this is an extremely simple neural network. We can make it much more complicated by doing all kinds of things. So one thing we could do is that actually we could make this into a multi-layer perceptron, if you will. We could make it into a deeper neural network. So what we've done so far is to basically have one layer. What does that mean? Well, if we look at our forward pass, we have our y's. The outputs is the effect of our inputs multiplied by one weight matrix here. Okay, but what if we take the output of this and put it in as inputs to another neural network? What do we mean by that? Well, let's just say we have W1 and B1, and we do W2 and B2. Oops. And instead of letting the first network give us 10 numbers, let's say we give us 206 numbers instead. And then we have 206 biases. And then we let another network take these 256 inputs and give us the 10 outputs. Okay, bear with me. So we're adding a second layer, basically, to this neural network. So here we have the first layer. And then we take our, then we need to have a activation function. What does that mean? Well, just like we had a sigmoid before, we don't just want to input the output of this first layer, but we want to run that through a activation function. We could have run sigmoid, but there are many different activation functions that we're going to use a reloop because we have learned empirically that they work better. So then we run it through this second layer, and now we have our 10 numbers. This is obviously going to run a little bit slower. And we're still doing 5 epochs. And while it's doing that, we can see if we can figure out how many parameters we actually have here. So the number of parameters, basically how many individual numbers do we have to optimize in this network. And so how many numbers is W1 and W2? Well, it's 784 times 206. And then we have 256 B1s, and then we have 2,560. Multiplying this number by 10, and then we have 10 B2s. So what is that? Well, we can actually calculate that by taking the sum of this. So it's 203,000 parameters in our network. Okay, so here we can see it started at a really high number and then it went down. And let's just see if it's better. It doesn't have to become better, but let's see if it improved. It's just a more complicated network, and just because it's more complicated doesn't necessarily mean it has to become better. And in this case, it didn't. So we didn't gain much from doing that. But it was just to show that we can make these networks more complicated. And what it means is that we are just adding more layers to it. And this is what it looks like in code. We take the output from the previous layer, which is really this one, and use that as input. Oops, sorry, as input to the other layer. Okay, so that's our image classifier. We're now classifying all these images. So that's great. Okay, so next step is to do a image generation. We're gonna generate images. So we're gonna do a GAN, which is also called generative adversarial network. And what are they? So a generative adversarial network is something pretty cool. Essentially, it's 2 networks. It's composed of 2 networks. One network is a generator. And that's basically a neural network that take a list of random numbers. And from that list of random numbers, generates a new image. If this is for images, it's going to generate images. So it generates new images that look like images that it's been trained on. Okay, so we're going to show some network some images, and we're going to train it on these images, and it's going to generate something that looks like those. Okay, so how do you do that? Well, you do that together with a discriminator. So the other network is called the discriminator, and the job of the discriminator is to tell whether or not the generated image or a image is part of the real data set, the one that we're training it on, or if it's a synthetic image, something that's been generated by the generator. Okay, so we have a generator generating new images and a discriminator trying to tell whether this is a generated image or a real image. And we're going to train them at the same time. And how do we do that? Well, let's first just declare these networks, and we're gonna cheat a little bit. We're gonna use Copilot to do this. If we are lucky, it will do that for us very nicely. So here we have one network. I suppose before I can do that, I need to show what this is actually doing. So let's start with some refactorization again. So this is our network. We defined a bunch of parameters. We can say how big it was. Let me remove that for now. But this is not the only way of doing it. We need to still treat these kind of parameters and the B's and the W's and whatnot. We need to include these, what the network looks like in our kind of training loop here. But we can do it much nicer using module in PyTorch. So we can create a classifier, and it's going to be a module. And we're gonna declare two functions. This one is the init function, another thing is a forward function. And what we're doing here is basically it's doing it for us. So it copied our initialization of weights here and put it here. So the init function is what's called when we create the classifier. So this is initializing our parameters. And then the forward function, it completely misunderstood. So let's create our own. And we do this, and we take it this way. And here we use Y, but we can actually just override X, because that's typically how you do it. Sorry. So we have X equals X at W1, X, 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 and we return X. So we just keep X here all of the time. So we run X, which is the input to our network for our first layer, and then we run it for the activation function, and then we run it for a second layer, and that will be our output. Okay, and then we can create a classifier, which will be our model like this. And we don't no longer need to use parameters in this way because they're all in our class. Okay, and then we can use this in this way. Y equals model X. Okay, now we don't have any parameters here to directly, but instead what we can do is say model 0 grad, because this is typically what you do. But for this, we need to actually get the parameters from our model, which we do this way. So this will do the same thing. We don't need to run it. Let's just make sure it works, and it works. It's going to run and take a little while. So this is just another way of kind of expressing. Sorry, this is not going to work very nicely at all. Because this is use self.w, self.b, self.w2, and self.b, because they are the ones we declare here. Anyway, so this is just another way of expressing our neural network, which makes it very simple to use it, because then we just get a model that we can use here. Okay. So that's what we're going to do for this generator. Okay. And perfect. Okay. This is not great, but it's not bad. So what we got now was basically similar to what we've seen before. We have, this is the first layer, this is the second layer. It will take 100 numbers. So we're going to let our generator take 100 random numbers. This first layer will generate 256 numbers. These 256 numbers will then run through a second layer that gives us 784 numbers. And that happens to be 28 by 28. So they will give us the pixels of our image. So the output of this will be the image. And then it declares it like this. And it says that we're using the first layer goes from a ReLU activation function, and our second layer will go from a sigmoid activation function. We're actually going to adjust this a little bit. And we're going to change it using something else. So since you typically declare a lot of these layers in this way, there is a much more efficient way of expressing that. That's using something called, linear layer 1, which is linear that takes 100 numbers in and gives us 206 numbers. So that's the same as this, basically. And we get the same with L2. And it would give us takes 206 inputs and give us 784 outputs. And we don't need this. How do you run through this? Well, you just use it as a module like this. We have ReLU here. Instead of this second layer, we use self.L2 of X. So this is similar. And this is typically what you want to do. You want to just, take X through L1, and then the ReLU, then take X through L2, and then another activation function. It's kind of a sequential thing. So, and again, instead of writing that every time, there is a module for that, which is called sequential, and it will just take these numbers. But we'll just copy these, which will give us a nice sequential program, if you will. But then we're missing our ReLUs. So there's also a relo, and there's also a sigmoid. And now we can say that x equals main.x. And that's the whole forward function. But like I said, I don't want to have a sigmoid here because it's empirically proven to work much better if you use a tanh, which is another set of activation functions. And you can all look them up later on. We'll look at a different video. Okay, so this will be our generator. I know that this is not going to behave very well. So what we will do is I will modify this to generate probably 206 will give us 256, and through another network 512. This will take 512. So we have 3 layers now. The first layer takes us from 100 numbers to 206 numbers. The second layer will take 206 numbers to 512 numbers, and those 512 will be turned into our pixels. Okay, and I think that will behave okay. Then we will define our discriminator, and that will now do kind of the opposite. So it will take the pixels for our image, 784, turn it into 512 numbers. If we take those 512 numbers, turn it into 256 numbers, and then we'll take those 256 numbers and turn it into 1. So what is that 1 number going to do? Well, that 1 number is going to be whether or not this image that is being shown is part of the real data set or not. Is this a real image or is it a generated image? If it's a real image, it's going to be 1. Just gonna say whether or not it's real. And if it's fake, it's going to be 0. So sigmoid is good for that, since that maps it to a number between 0 and 1. And pushes it towards 0 and pushes it to 1. So then we can define these. So we have a generator G, and we have a discriminator D. So G and D are now basically functions that we can use. So to run this, we can, if we have some noise or random numbers, right, we can run G on this, or on noise. Okay, so this is a fake image, a generated image, and we can show it. We can look at this image. This is an image that we have generated from our generator. Okay, it took 100 normally randomly distributed numbers. We get a fake image and we can see it. Okay, so this is obviously not something that looks anything like our MNIST dataset, and we're going to train this to generate images that look like our training dataset. So we're gonna have to do something about that. We're gonna have to train the network, obviously. But we can also run our discriminator on our fake image and see whether or not it's real or fake, and it gives us 50% chance that it's real. So it's obviously not trained and it doesn't know anything. 50% is not really giving a good recommendation, I think. Okay, so then the question is, how do we train these networks? Well, the way we are going to train a generative adversarial networks is, first we train the discriminator, and then we train the generator, and we do them through mini batches. So the discriminator for one image batch, and then the generator, and then we do it again and again and again and again. Okay, so how do we then train the discriminator on these batches? Well, let's first just go through our mini batch. So we can take our data and our labels. Actually, this is our images, and our labels we don't care about for loader. So this will be our inputs, and we can say that this is these images is actually going to be reshaped into just one long vector. Instead of 28 by 28, it's going to be 784 numbers. Okay, sorry about all the bad stuff. 4 images in loader. So this is our real images, and then we want to get our output from our discriminator on our images, right? And we want here that our outputs should be 1, because these are real images. So we want the discriminator to say that these are real images. Okay, so we want to write a loss function. This is our objective function. It's going to be the loss function for real images. It's going to be binary cross entropy. We used cross entropy before for several classes. When it says 2 classes, it's going to be cross binary cross entropy. And we want our output to be 1s. That's what this line is saying. Okay. So we want our loss to be binary cross entropy where outputs should be the ones. Okay. And then we want to create some noise. Then we want to show it some fake images. So we generate some noise. And we generate just the number of fake images as we have real images, which is 32, because that's our batch size. We can write batch size here if we want. Then we want to get our fake images by generating from the noise. So this will be our fake images. And then we get our output from our discriminator on the fakes. And then we want the fake loss to actually be, again, binary cross entropy, but where we want the outputs to be zeros. So that's how we can read this. Okay. So we want so basically what we're saying here, when we show fake images to this discriminator, we want the output from the discriminator to be zeros. And when we show real images to the discriminator, we want that output to be ones. Okay. And then we can now combine this loss to just be the real plus fake, because we want both of them to be low. If one is high, well, then loss will be high, and we can optimize that. So we want both of them to be low. And then we want D to be 0 grad. We want to run backwards. So now we want to train our discriminator. So we run gradient descent on a discriminator. So this is how we train, right? So we got the real images. Then we train it on fake images. And then we do backpropagation and gradient descent for the discriminator. So then we're going to do the same thing or similar thing for our generator. Now we're going to optimize the generator. So this will only change the parameters of our Ds, of our discriminator. So how do we do this for our generator? Well, what we do is that we generate some images, some fake images, and then we get the output from the discriminator. Okay, so we run the discriminator on our fakes that we generated. But now we want to optimize such that the output from our discriminator thinks that these images are actually real. So we're saying that we want to have loss to be the cross entropy between our output and ones, because we want to optimize the generator such that it fools the discriminator to think that these fake images are real. That's what this is saying. Okay, so now we have the loss function. We can do 0 grad, we can do our loss backward, and we can do gradient descent. Okay, and this is done for all the images in our dataset. So let's just see what happens here. Let's just run this, right? No, batch size is not defined. I thought I did define batch size. Anyway, let's define batch size. What I had. Sorry about that. What else have I forgot to do? So now this is running it on all the images. It's training the discriminator on the real images and the fake images in one sort of backpropagation and gradient descent loop, and we're doing the generator in the same way. So the discriminator will improve here, the generator will improve here, the discriminator will improve here, the generator will improve here, and so on and so forth, right? So now let's see what an image might look like. Something is happening, right? It's not just noise anymore. We can see that there's something in the middle. Perhaps this is a 0 or this is something else. There's something happening. So let's see if we can see what's actually happening as it's doing this. And one way we can do this is okay, we can do a learning rate, sure. Don't know what the learning rate is 0.1 here. Okay, let's do that. But what we can do is that we can create some static noise. What I mean by that? Well, it's just noise that's not going to change. So let's do 4 of them. So we create 4 sets of static noise. Okay. And then we let this run for not 10, but actually 100. So this is going to have to run for a while. And then after each epoch, we want to show what these images look like. So what this is doing is it's taking the static noise, generate some images on it, and the static noise will be the same the whole time. So it will show how it generates from the same random numbers as it learns. And then we're going to create a plot where we show these images, basically. So let's see what happens if we run this. And I want to initialize it randomly first. Let's see what happens. So as we saw before, it took a while to run it one iteration. Once it's run one iteration, we should be able to see it. Okay. So here we got the first 4 numbers after the first iteration. So I don't know if you can see anything here. Maybe this is a 9, maybe this is a 6, maybe this is a 4, maybe this is a 3. Okay, but it's a little blurry. Run it again. It's getting slightly better. And as it runs through this, hopefully it's going to be better. Perhaps going to get worse at some points as if the discriminator happens to become better than the generator and the generator struggles, or perhaps the opposite, actually, that the discriminator gets bad, so the generator actually can just generate rubbish, and the discriminator gets fooled by that. So what we have to do is make sure that the discriminator has to be really good. What we can see here is actually the only place where those real images, so we are trying to generate images that look like the real images, but the only place that the real images actually exists is here. So it's only when we train the discriminator on real images that any image is actually even apparent. We never show it to the generator. The generator never sees, it's never exposed to the data that is the real images. It's only exposed through that, through how the discriminator is able to say that this is a real one or not. So the real images are here for training the discriminator. But then in order for the generator to generate images, we are using our discriminator. And that's what we're optimizing on. So let's see how it goes. Whoa, something is oversaturating. So as you can tell, things are happening. We're getting numbers. I'm not sure what's happening here. This looks very interesting. I think actually I have a slightly too high learning rate. So maybe we should stop this and see what happens if we lower that a little bit. So set it to 0.01 and then we'll reinitialize again. And let's see what happens. And now, as you can tell, we are running this on fairly simple data sets. It's only 28 by 28. And it's a small set of numbers or images, classes of images it's going to look like. And yet it takes quite some time to run it, to generate these images. But it is working. It is giving us something. And if you have larger data sets, more complex images and stuff like that, it will obviously take longer. And it might also be much, much harder to do this. It's also interesting to see that our generator it doesn't know anything about images. It's just the way we are interpreting the numbers it's outputting. And also, of course, the numbers that it's being shown or input to it, especially to the discriminator, that's where the information about images exists. But there's no information in the network that says anything about images. But essentially, this is what I wanted to show. We've now shown, let's go to the start. Hopefully now you should know what the neural network basics are, right? So we have inputs, we have outputs, and we have weights and biases. And actually, we could just change that to say we've learned about parameters and what they are. Yeah, we learned about backpropagation. It's basically a call to backprop, right? Or backwards. But that's what it is in practical terms. It calculates the gradients, and then we can use those gradients to do stochastic gradient descent. And it was stochastic because we had a mini batch. So that's what you learned. And then we use basically the same neural network as we did here to train the network, to classify images. And then we used essentially the same sort of network, although we did 3 layers instead of, we tried 2 layers in the classification. We used 3 layers, both for the generator and the discriminator. And that is called generative adversarial networks. A generator and discriminator improving together and trained jointly, if you will. And so we can just see if it's improving. It should be improving. It's going to take much longer to get to nice results. But in the end, the background is going to be more black. The image is going to be looking more like numbers, and you can fool the discriminator and maybe even your friends. So with that, I'll say thank you for watching, and until we see you next time.